So I'm going to start with sharing my slides, and these are the slides that you also have on Canvas. So if you want to kind of download them from Canvas, then except from slide 2, every other slide you do have. So we're going to continue about talking about the filters, more or less a continuation of the last talk we had, and also a little bit about the talk or by the presentation you got by Connor and Esther. Here I also give you some additional resources. As you know, the textbook, chapters 15 to 18 are good resources. Then my lectures that are online on YouTube, lectures 9 and 10, are very appropriate for this section. And then the two papers that we are kind of discussing in class. One of them we already had, and the other one we will have after the weekend on Monday. So I want to kind of start by indicating refreshing your memory. If we have an LTI system, a linear time invariant system, also called a filter in our case, or a model, we know this system because it's linear and time invariant by its unit impulse response, HT, lowercase h, or the transfer function, which is the Laplace transform of lowercase ht, indicated by capital HS, or in this case, more appropriate when you talk about filters, the frequency response hj omega, where omega is 2 pi times the frequency in hertz. So if we know this frequency response, we basically know the filter. And we get a value for hj omega for each value of omega. So that can be represented in the Argand plane as follows. We have the real axis and the imaginary axis. And for each frequency omega, we have kind of a value, a complex value. That complex value is characterized by two properties. Its size, hj omega in between the absolute signs, and phase, in this case, indicated by phi. And so we have that for every frequency. And if we kind of describe what these values are for each frequency, we basically know what the filter is. If you know the expression, you can do the inverse Fourier transform, and you will get the unit impulse response. I mentioned that this is usually, and that's kind of where I ended last talk or last lecture, is that we can kind of present this in a Bode plot or in a Nyquist plot. And in the book, I'm using a MATLAB routine to do that. And these MATLAB routines you can download, as you know, from the book's website. And you can run this thing. In this case, we were looking at an RC filter, an R of 10 kilo ohm and a C of 3.3 microfarad. And so these are the filter components, and the product of that is the RC time of the time constant. We also derived in the book what the presentation or what the value is for hj omega, and we can then compute, as we can see in the previous one, if we know what that is, we can compute its size and the phi. Its size is indeed indicated as the amplitude here for each frequency. And then the phi is basically the invert tangent from the imaginary and the real part. So now for every frequency, in this case I go from 1 to 5,000. For every frequency I can compute the size of this hj omega and its associated phase. I also compute here the minus 3 dB point, which is kind of a value that characterizes the cutoff frequency. So then we can plot that. We can plot it in the Bode plot. And in the Bode plot, we kind of separately plot the size and the phi basically in two plots. And then in the Nyquist plot, we do that in a polar plot, and we do that in one. And in the book, this is figure 17.4. We have these Bode plots which is here, the frequency versus the output and the phase, the input, output, and the phase. And here you can see the Nyquist frequency or the Nyquist plot in the Argand plane. So basically, this is also what this MATLAB routine will give you. Now we did, and we didn't do that this year. We did do that on previous years. We actually built this filter, and then we measured the ratio between input and output for different sinusoidal frequencies. And these are the dots that you find here at different frequencies that we tested. If you want to see these measurements, they are actually also part of the book. It's in a table in chapter 15. Now, if you want to kind of check this against the theoretical frequency, which is this one, then you can see that we did a pretty decent job in kind of predicting what was going to happen. So there is a good agreement between theory and practice. There are a couple of deviations, but that's because we were measuring this on a pretty small oscilloscope screen, so the precision of our measurement was not that great. Had it been more precise, then obviously we would have done a slightly better job in fitting the observations with theoretical prediction. So that kind of concludes the part that I needed to talk about before we focus on digital filters. I somehow do not see my chat box. So if you do have, let me see if I can see. Okay, I do not see any additional, I have my chat box now, I do not see additional questions and I don't hear anything. So in that case, we just will move on to digital filters. And the digital filters are kind of described in chapter 18. Recall that these are characterized by difference equations, not by ordinary differential equations, such as the ones in continuous time. And these difference equations are basically characterized by a bunch of coefficients related to the output of the filter y with different lags k, and a number of coefficients associated with input x, also with different lags. And of course, some of these lags can be zero, and some of these coefficients can be zero as well. Now you can transfer this thing into the z domain pretty easily. Then we have this becomes capital XZ and this becomes capital YZ. And then since we have then the lags characterized by Z to the minus K, same thing here, we can simplify this equation into the one you see on the second row on the left side. And then if we divide YZ by XZ, which is basically what we showed in the Laplace domain and in the frequency domain, the convolution becomes a multiplication, or in this case, if you want to kind of determine what HZ is, it's the division of YZ by XZ. You can see it is nicely determined by these coefficients A and B. So in this case, you would know the digital filter completely if you knew all the coefficients A and B. And the interesting thing is that, or the good thing is that in the literature, also in the book, and also in MATLAB, these A and B coefficients are indeed also called A and B. So that's makes life easy. By the way, this expression for HZ is sometimes changed by dividing by A naught, and then you get the expression in the lower part. But that's just kind of a different way of presenting it. It's the same thing, of course. Well, there are multiple types of digital filters, and one of the types that we can have is an infinite impulse response and a finite impulse response filter, IIR and FIR. And I give you two examples here. This is an example of an IIR filter, and this is an example of an FIR filter. And we're going to look at some of these examples a little bit further down the road as well. What does it mean? Well, IIR means that whenever you give that filter an infinite or an impulse response at its input, its response will kind of continue to infinity. And the reason is, if you look at this equation of this IIR example, is that you see that the output at time step n is always somewhat dependent on the output on step n minus 1. So that means that as soon as there is a response to a unit impulse, then the next one will at least have some part of it, and then the next one will have a part of that, and the next one will have a part of that. So I sometimes compare this with a perpetual stew, isn't it? If you have a stew at home and you eat from the stew, one of my children is a professional chef, so that's the reason I think that's appealing. But you have that stew and you eat the stew, but not completely. Then you add new components to the stew. So some of the previous stew is still in the new stew. And then you eat that, and then you do not completely finish that. And then you add new stew to that. So there is still then in that new stew a little bit from the first and the second stew, etc. So in that sense, even after you would do this 100 years, there probably would still be a few molecules over from that part. So that's kind of an infinite impulse response. It never completely disappears. The other one is a finite impulse response, and that's the exception or the example here in the green window. You can see that as soon as, since the output only depends on current input and 2 steps behind, that as soon as there is no input related to the unit impulse anymore in the xn minus 1 and xn minus 2, there will not be any output related to that unit impulse at the input in the past. So in that sense, you get a finite response to that. This is kind of a distribution or a classification that you often see in the more engineering literature. There's another classification that's called AR, MA, and ARMA filters. And that classification kind of overlaps with the one we just discussed. An autoregressive filter, an AR filter, and an example is in the first equation, is that the output at time step n is dependent on previous time steps, and capital A and B are some coefficients. And the question is, in this case, is this an IER or an FIR? And since it's a bit difficult to have a discussion here with the Zoom, I will answer that question. Since there is always a little bit of the past in there, of course, this is an infinite impulse response filter because it will never completely die out. The moving average, on the contrary, that's kind of an, let's say, the sum of some input and some previous inputs divided by some sort of a coefficient A. That's of course a moving average because it averages 3 points and then it moves to the next 3 points, it moves to the next 3 points. So that's why it's called a moving average. Of course, in that case, we deal with a finite impulse response because after the input is not present anymore of the unit impulse, then there will nothing be about that in the output yn. And then, of course, we have a combination of AR and MA, which is that the output depends on the previous output, but also on the current and previous input. And so that's a little bit of both. But as long as there is some part of a previous output in there, of course, it is an IIR type filter. And ARMA filters are actually the one that we looked at, for instance, the RC filter. If you look at the concrete time version of that filter, you will find that that is an ARMA filter. Moving average filters are very popular because they are essentially stable, always stable, whereas the other filters are not by definition always stable. So they have a somewhat higher preference in the literature. In one of the papers that was just presented, they said that there were no artifacts related to that. As we will see in a little bit, that's not entirely true. But it is, of course, nice because they're always stable, and they can be used for high pass and low pass filtering. So let's look at why this moving average filter is not always as ideal as you might think. So you have to be a little bit careful with that. Let's look at a filter, this one, that has an output yn, which is the moving average of 3 points xn minus 1, xn minus 2, and then divided by 3. So at least it is a causal filter. We could make it also non-causal, of course. Then it would be xn plus 1, xn, and xn minus 1. Then it would not be causal because it would be depending on the future xn plus 1. But in this case, I took a causal version. Now we're gonna z-transform this thing. So yz is the z-transform of yn, and xz the z-transform of xn. And then basically we get the expression that you see here. Yz is xz times 1 plus c minus 1 plus c minus 2 divided by 3, because 3 is the constant. And then yz over xz is the transfer function, and you can see what that is. And you can then simplify that a little bit. You can use basically the algebra to do that, and then you say, well, we know what z is. Z is basically the e to the power s. But since we are interested in frequency, we kind of substituted by e j omega tau, which is what we did. And then you kind of can go from hz to hj omega. So here we go from transfer function to the frequency response. Using Euler for the cosine, you can simplify it a little bit, the expression, although that's not necessary. It's commonly done. So now we have that expression. Hj omega is this complex exponential times this cosine plus 1 expression. Now we have to think a little bit. How do we interpret this? And you have to realize now that tau in this case is the sample interval, which means that 1 over tau is the sample rate, and half of that is the Nyquist frequency. And so for the filter, pi over tau is the Nyquist frequency in radians per second, because you have to multiply the frequency by 2 pi to get the omega, the radial frequency. So now you see that we kind of did steps to go from the discrete time domain to the frequency domain. So we can see what the relationship is between time domain and frequency domain, and we can actually plot that. You can plot that in different ways, but here you see the MATLAB lines that I use to plot this. This is the omega that we just said. Well, it's going from 0 to pi over tau. The amplitude ratio is the value that we just that expression that we just kind of derived in the previous slide, the lower expression here. And we take the absolute value to kind of look at the magnitude, and then we plot the omega and amplitude ratio in this plot on the left side. And there you can see that indeed, as you expect, you have a low-pass filter That's not surprising, isn't it? Because if you smooth stuff out, you get rid of some of the higher frequencies. But what you can also see is that this filter is not totally ideal. Its slope is not that steep. And it has side lobes. I mean, if you look at this part here, after 2 rate per second, you can see it's not flat, it's kind of coming up. And depending on what the values are that you use in your smoothing filters, you will always have side lobes. So you have to be careful that you have situations where you really don't care too much about side lobes. If the peak of your side lobe kind of coincides with, for instance, 60 cycles, you may not have a very good procedure to filter your data. So be aware of that. Be aware of that. That's kind of the situation. And if you have a smoothing filter, kind of do this procedure. Kind of take your expression, make the Z transform, substitute your Z for AJ omega tau, and kind of make this plot and see how it lands in your particular frequencies. That's kind of an important thing to do. Now, MATLAB has really nice tools to make and evaluate filters, and that is an example that I give in chapter 18, and this is figure 18.2. And here I'm using a filter to do something that you actually should not be doing, which is to get rid of 60 cycles. As you know, and I told you several times already, it's not such a good idea. It's a way better idea to get rid of your 60 cycles by proper grounding and shielding. But I have an example here and you can load that too. You load hum. And that's a file that has some EEG data that is sampled at 256 Hertz. But the technician did not pay a lot of attention to grounding, and there is a huge amount of 60 cycles in that data. So what you now can do in MATLAB, you have a bunch of very, very useful functions. One of them is called butter. That's kind of not to create butter, but to create a butter word filter. And in butter, you can basically describe how you want to filter, and then it will create the coefficients B and A that we just discussed in our equations in our difference equation. So butter, for instance, here it says butter 6, which means do a sixth order, which means make the slope relatively steep. Go from 60 minus 5, so 55, to 60 plus 5 to 65. So it goes from 55 to 65. And I divide by the Nyquist frequency. And the Nyquist frequency is half of 256. And it has to be a stop band filter, not a pass band, not a low pass, but it has to be a stop band filter. And then what the nice thing is, you can kind of create the Bode plot for that filter, because if you know the B and the A coefficients, you can use the fracz command, and then you get a Bode plot. See, you can see, oh yeah, it's a very nice filter. In panel A, it's a very nice filter. You can see it cuts in these nicely around 60 Hertz. It has awkward phase shifts that you can see as well. The other thing is you can look at the unit impulse response. You can already see that this is an infinite impulse response filter. You can see in panel B what the unit impulse response is. But in panel C, you then finally see what the purpose is of this filter, which is to get rid of this awkward 60 cycles. In blue, in dark blue, you see the original recording. And you see that it's very difficult to distinguish what is going on there, because it's so, it's kind of one thick artifacted recording. And then in red, you see how the notch filter, this digital notch filter, is cleaning up the signal. Be aware, though, that when you do this, that sudden changes can lead to oscillations, ripples in your recording. But there are not too many really steep changes in this one. So I would not, in this case, I wouldn't be too worried about that. That's kind of one example of how you could use the filter. And as you can see, it can do a spectacular job in the sense that it can make a totally unusable recording into something that you can at least interpret. You see, there is one new message. Alan is asking, is B over A the impulse response of the filter? And the answer is no. But you can kind of compute the impulse response to the filter. You should probably think about how to do that, because you have, in all the examples that I gave you, you have the opportunity to do that. And if you fail, you can ask me later, but I want you to think about that first. But it's a good question, yeah. So in both cases, you will know the filter completely, whether you know the B and A coefficients, or whether you know the impulse response, or whether you know the frequency response, or whether you know the transfer function. I'm going to finish up with two examples. One of them is in figure 18.3, where there is a practical example on how filters can be applied. And this is one of the, I would say, most successful implants that we have thus far, which is the cochlear implant. It's kind of suitable for people that still have an intact cochlea and an intact nerve system, an eighth cranial nerve and system in the brainstem and the brain itself to interpret noise. So if the problem is more in the external parts of the auditory system, this is an extremely efficient implant. The way this works is kind of based on the biology of the cochlea. So if you have the cochlea, which is kind of like the house of a snail, isn't it? In the base part of that snail house, you have detection by the hair cells of the more higher frequencies, the higher tones, higher frequency tones. Whereas in the top of the cochlea, it's more the lower frequencies that are being detected by the hair cells. And the system basically takes advantage of that. It puts in an electrode in the cochlea that can stimulate along the kind of the windings of the cochlea, so both the base and the top and everything in between. And now what that system is doing is basically it helps to detect the different frequencies of the sound by using filters. So if you have a microphone, as on the right side, you can see a microphone picking up a sound. And this sound, in this example, consists of higher frequencies and a bunch of bursts of lower frequencies. What you now do is you have a filter bank, and in this case, they only show 4 filters, but you can have, of course, multiple filters in this filter bank. The top filter basically filters out the high frequencies, and then you get lower and lower and lower frequencies. And then you have another filter-like structure that determines the envelope of these frequencies. So you can see the envelope of the high frequencies in the top panel of the middle column, whereas the lower frequencies envelope you can see in the lower part. And now you have a pulse generator that creates pulses to stimulate the hair cells in the cochlea according to the envelope as it was detected. Which means that, of course, in the end, you get, if you have high frequencies, you get stimulation of the high frequency part of your electrode, which is at the basis of the cochlea. And you get the low frequencies stimulation represented at the top of the cochlea. So it completely mimics the biology of the system, which is probably the reason why it is so successful, because if you implant this into someone who is deaf, they can almost immediately hear. So the system is so used to kind of work with this type of stimulation that it kind of goes from being deaf to being able to hear. For the visual system, people have been looking at similar implants, but one of the projects is actually going on at the U of C and MIT or IIT. But thus far, it hasn't been as successful as the one for the cochlea. And then the last example is applying filters in the spatial domain. In this case, a photograph. This is a picture of Lena. Lena is in a pin-up, but they always show you the decent part of the pin-up picture. You can find this picture anywhere where there is spatial filtering or spatial analysis going on. It's kind of a standard test image that people use to show how their algorithms are working. So you may find that Lena is appearing in many textbooks and many other publications where people want to show their the purpose of and the performance of their algorithms. In this case, we used, and this is figure 18.4, we used a high-pass filter to kind of go over this picture. And as you can see in the results in panel B, that high-pass filter is such that it mainly detects the edges, and which is of course what you expect for a high-pass filter, because it looks at sudden fluctuations along the lines of the image. And you could of course later superimpose B on A, and then you would have an enhanced edged picture of Lena. And you could kind of use the same filter for whatever type of image you have, and test these things out. We will get back to Lena when we talk about some other analysis, probably later when we look at wavelets, because it's used a lot in wavelet analysis as well. And with this, I would like to stop the recording, and again I will hang on for questions on the basis of this or previous stuff.